Hey y'all, so when I left you guys off last time, I left you guys with this question here, right? So I left you guys with this question. We said that you are hungry, you decided to go spearfishing, this could have been me in this example, and you're trying to shoot this fish, or spear this fish, and you got to figure out, do you want to aim directly at the fish, a little above the fish, or a little bit below the fish? And I asked you guys to use this, just a simple straw or stick, something straight in a glass of water, as a piece of evidence to support your reasoning for this. Now, one of the things I hope that you guys noticed is, especially if you were to look at like straight down the stick or straight down the straw, right? If you looked at it out of the water, right, it should be pretty much straight. You shouldn't really be able to see the end of it. But as you stick it in the water, you may notice something very, very strange. You start to be able to see the end of the straw. It's almost like it's coming out away from where it normally is. And you could kind of diagram it as looking like this, right? So we know that that is a straight stick or a straight straw, right? And so we know it's actually in a straight line, but as you stick it into the water, what happens is where the air meets the water, where that surface of the water is, the straw starts to kind of bend outwards, right? So we can actually see more of it. So if I'm looking straight down the straw there, I can actually see the very end of it, right? So this is where the straw seems to be, and this is where the straw actually is. So if we're thinking of this in terms of the fish that we see, right, this is what we actually see. This is the fish that we actually see. The actual fish itself, then, must be below that point, right? So if I'm seeing a fish here, just like I'm seeing the straw there, that means that the actual straw, the actual fish, is below that point. So if I consider here, where would I actually need to aim? Well, it turns out that I would need to aim a little bit below the fish if I wanted to actually get it, right? So that's where I'd need to aim in order to be able to stab the fish. Now, why is this, right? What's actually going on here? Well, if we think of what we know with array diagrams and how our eyes actually see kind of where things are, if we think of it in these terms, if I'm looking here and I'm seeing the end, I'll just go at the end of the straw right here, right? And that means that that is the line, right, that my eye is actually following. It's being right there, right? It is seeing the this surface right here, this point on the surface, right, as being where the kind of the straw is on the surface of that water. So if I erase this guy, right, my eye is seeing the straw. Oops. My eye is seeing the straw as being right kind of there, right? It's following that straight path. But the straw is actually right here. So what that means is that the light kind of reflecting off this piece of the straw is going up to this point, and then somehow is going from that point to my eye, right? So at this point here on the surface of the water, right, the light that's reflecting off this bottom part of the straw goes up to that surface, and then you'll see here it actually, instead of continuing to go straight up, it actually turns, and so my eye interprets that as being back here. It kind of follows that straight line back to right there. So what's actually going on right here at this point where the light is actually bending, right? Well, what we have here is what we'd call refraction, right? Which is simply the bending of light, right? When it goes from one medium to another, right? At an angle, light can bend. You may have noticed if you held your straw just straight up and down, right? Nothing really happens, right? It kind of looked just perfectly normal. So it has to be at an angle. Those light rays have to be coming in at an angle, and they can actually bend. And that gets us to our first idea of what refraction is. So here, once again, here are the goals that we're kind of looking at, things we're trying to understand. When objects sometimes look different when we look at them through different materials like glass or water. Does light always travel at the speed of light, 300,000 or 300 million meters per second, 78 meters per second? Does always travel in straight lines? How do we explain and predict how light bends or refracts through different mediums? What is total internal reflection, and how do rainbows work? So those are the questions that we're hoping to be able to answer. And we'll start with this first one here. What is refraction? All right, so refraction is when light waves bend, right, or change direction when or material, we'll just say one material, to another at an angle. Right? So that's what refraction is. So when that light bends as it exits the water, right, that's refraction. If you think of what light does in a prism, that's refraction. Okay, like going through like a lens, like this magnifying glass. We'll talk more about these next class, but that is also refraction as well. Okay, so when we have light waves bend or change direction, we're going from one material to another, and it has to be going from one material to another at an angle. That's what part of what causes the bending, but it's that bending of light. Now, in order to understand how light refracts, one thing that we have to know about is this thing called the index of refraction, right? So in order to understand this, we have to understand that light does not always travel at the speed of light, right? In fact, as light travels through a material like this lens, like through a prism, like through water, it actually slows down a little bit, right? And why it slows down is because as light travels at 300 million meters per second in a vacuum, so with no other materials, no other molecules or atoms to interact with or to kind of disrupt its movement. But if we actually have atoms with electrons swirling around them, those electrons that are moving around them can actually slow and interfere with that wave, and they can slow it down. That wave can still pass through them, right? It can transmit through that material, but it oftentimes gets slowed down. And that's because these electrons, kind of acting like springs, they get kind of jostled, they absorb some of the energy, and then they re-emit it, and so they kind of pass it along. But they pass it along at a slower speed, right? Every single time that a molecule kind of absorbs this light and re-emits it, in order to pass it along, it slows down the overall speed of that wave of light. Right? And so you could imagine that the more atoms that we have packed in somewhere, the more and more it slows it down. So air, right, relatively not that dense, might not slow down light waves as much as water, for example. Water is a little bit more dense, so it'll slow down those light waves more. In a vacuum, there's nothing to slow them down, so they travel at the kind of honest speed of light. So the index of refraction, right, is a measure of how much light slows down when traveling through a material, right? And there's actually an equation that we can use to calculate it. N, which is it's our symbol for the index of refraction, is equal to, lowercase n, is equal to c, the speed of light, divided by the velocity that it's traveling through the material. So we could write this out as the index of refraction equals speed of light in a vacuum divided by speed of light through material. Right. So that's what the index of refraction is. It's a kind of a ratio of the speed of light in a vacuum to the speed of light through that material. So it talks about how much the light slows down when traveling through a material. And that's known as the index of refraction. That actually becomes very useful when we start to make some calculations about refraction. I'm not expecting you guys to memorize or remember that, or I'm not going to quiz you guys on it, but it's just kind of good to know exactly what's happening there, and it comes up later. So if we look at the index of refraction of a few common things, right, in a vacuum, there is kind of no index of refraction. It's still traveling at the speed of light, so the index of refraction becomes 1. Right? When traveling through air, it travels just a little bit slower. Right? Through water, it's 1.3 times as slow as it would normally be in a vacuum. And then in glass, it's about 1.5, depends on the type of glass. And then in something like a diamond, for example, which is relatively dense, right? Those atoms are in there quite packed. It goes almost 2.5 times as slow, right? Which is pretty incredible. So kind of what's important to know about this table here, right? The key thing is that light travels at different speeds through different materials. Right? Usually, the more dense the material, the slower light travels, right? And therefore, the higher the index of refraction. Right. And that's the key idea. So typically the more dense material that we get, the slower light travels, and we have a higher index of refraction. Okay, so one thing to think about is with refraction, with this index of refraction, in order to understand what's going to happen to that light when it goes from one medium to another, is we need to think, is that light going to be speeding up or slowing down as it goes from one medium to the next, right? So for example, if light is going from water to air, right, a higher index of refraction to a lower index of refraction, right, here it's moving slower, here it's moving faster, so it's going from slow to fast. If it's going the opposite, if it's going from air to water, it's going from fast to slow. Okay, so that's important to keep in mind. It's slowing down as it enters that new medium, or speeding up, depending on which way it's going. What angle is the light coming in at? This becomes very important because, like I said, in order for something to refract, the light needs to be coming into the medium at an angle. We'll talk more about why that is in a second. Which side of the light ray will change mediums and slow down or speed up first, right? So is it going to be, if we think of the light wave as having kind of two sides, is it going to be the left side or the right side that's going to speed up or slow down first? And then what does that mean, all of that, about how the light will refract or bend, right? So if we just look at our example that we drew in here, right, what's happening is we're going from water to air. So the light is going from a slower speed to a faster speed. And based on this angle that it's coming in at, right, we can imagine that the right side of this, right, is going to speed up a little bit more first, right? Because the light is going to speed up as it leaves the water, right? But the right side is going to exit the water first because of the angle that it's coming in at. So if the right side is leaving first, then that means that the right side is going to speed up more, which means that it's going to turn to the left, right? That's what those questions kind of mean there. That's how we can look at that. And to go a little bit more in depth, we can talk about this here, some kind of diagrams. There's a little simulation I want you guys to check out, and I guess we'll talk about that. So this is a nice little simulation. We can go through here and we can mess around with different materials, right? So I can go from air to water, right, as well as other things, and I have this little laser pointer. I can change the angle at which it's coming in at. Now you'll notice that as it goes through from one medium to another, from air to water, some of that light is reflected, right? And if we pull out our protractor, kind of put that right there, we'll see that if it's coming in at 30 degrees, right, it does follow the law of reflection, and it's leaving at 30 degrees as well, right? So in at 30, out at 30, follows the law of reflection. And this is why, for example, you can see a little bit of a reflection of yourself in water, right? It's because some of that light is actually reflected, but also some of the light actually ends up being passing through that water, and actually you can see it's bent, right? The reflection is at 60, but the refraction is not. It's not going straight through at 60. Now if you notice, if I take this down and I make it go from air to air, right, no change in material, and so it's not bent at all, right? The greater we make the index of refraction, you'll notice that the more that that light ray is bent, okay? So glass is going to bend more than water because it has a higher index of refraction, okay? So, so that's pretty straightforward, right? We'll notice that it always, in this case, as long as it's coming in at this angle, it's bending to the right, right? It's bending to the right, and that's because it's slowing down, right? So if we look at this as a wave, right, you can imagine, and this is kind of like looking at the wave kind of from above, you have the red parts represent kind of the peaks, and the black parts represent the troughs of that wave, right? And as it's coming in, right in this area here, right where it interacts, this right, or this lower side of the light wave is slowing down first, right? And because it's slowing down first, and it's going slower and the other side is going faster, that causes it to actually turn. And so it turns in this direction, okay? So if we look at this diagram here, right, we see this ray coming in, it's going from a faster medium to a slower medium, right? And so it's going to bend towards our normal line, towards this perpendicular, okay? It's going to bend that direction. Now, if we switch this around and we go from a slower to a faster, right? Now, unfortunately, in this case, we can't just like bring it down here into the water, but what we can do is we can say, hey, let's go from water to air. And now we can mess around with this. And what you guys will notice is if I keep this here at 30, right, some is reflected back into that water, but some passes through. Well, in this case, we're going from slower, right, to faster. So if we look at it as a wave, right, this lower side is going to speed up first. This other side is going to be a little bit slower, so it's actually going to turn away from that normal line. Right, so that's what we have here. When it's going from a slower to a faster, it turns away from that normal line. Right, so when going from a faster medium, right, N1 is big, or is N1 is closer to, or we'll say N1 is lower, or closer to 1. Going from a faster medium to a slower medium, we'll just say this, going from a faster medium to a slower medium, so we could say that N1 is less than N2, right, and that's the index of refraction for medium 1 is less than the index of refraction for medium 2. Then light bends towards the normal line, right, and when going from a slower medium to a faster medium, right, so in this case then N2 would be greater than N1, then light bends away from the normal line. Okay. Pretty straightforward, nothing kind of too crazy there. And the way that I like to think about it is it going from faster to slower, and then which side of the ray is hitting first, and then how is that going to react? And a good kind of metaphor or simile that you guys can use to think about this is if you're driving a lawnmower. Or you could also think about people marching in a line and going from one medium to another. Okay, so in this case, if I was walking my lawnmower along the sidewalk and then all of a sudden I get grass, well, when I get into the grass, that slows down how quickly the lawnmower can roll. So in this case, if the lawnmower is coming in at this angle, well, the right side of this lawnmower hits the grass first and slows down, so it can't travel as quickly. But this left side of the lawnmower is still traveling at the same speed. Well, that causes the entire thing to shift, right? When you have something that's moving along and one side moves slower than the other, that causes the entire thing to turn, to shift. Okay, so that's what's happening here. So if we're going from faster to slower, we turn towards the normal line, right? And if we're going from slower to faster, all of a sudden now the right side is able to speed up sooner, right? So the right side speeds up sooner than the left side, and so it turns away from that normal line, right? So we can say here we can visualize this as a going from a fast surface to a slow surface. Right. And you could think of other metaphors as well. Something that we probably would have done if we were in classes, we would have had everybody kind of link arms together, and then we'd have a line on the floor. And when all of a sudden everybody kind of got to that line, it would represent a different medium. And once you got to that line, you could either move faster or slower. And then as a whole, right, the entire kind of class in that line of people would bend as they go from one medium to another. Okay, so that's what refraction is all about. So once again, kind of considering those questions, is it speeding up or slowing down as it moves from one medium to the next? What angle is it coming in at? What side of the light ray will change mediums and speed up or slow down first? And what does that mean about how it will bend? Okay, so that's kind of the long and short of how refraction actually works. And there is there's actually an equation that goes over the exact angle, right? If we do notice, there is like an exact angle that it bends at, and that is tied to the angle of refraction, right? That is something that's called Snell's Law, right? And it ties the angle that the wave is coming in at and the angle that the wave is leaving at to the index of refraction for those two objects. Now, I'm not index of refraction. I'm not worried about you guys knowing that, but it is definitely a thing. You guys can look it up. It's called Snell's Law. Kind of cool stuff. And so if we look at this question, then why doesn't the light bend? The incident ray is lined up with the normal line. Does the light still slow down or still change speed? Well, if I take this back to kind of the waveform and I just go straight in, kind of remove my protractor there, right? We'll notice if it's not coming in an angle, then neither side of the light wave is speeding up or slowing down before the other. So it continues going in a straight line. However, it does definitely change speed still, right? And that is an important thing to keep in mind. But if one side of the wave can't speed up or slow down before the other, then it just keeps going in a straight line. Okay. Now, if we consider here, this, going back to this example here, so we talked a little bit about how when we look at it straight down from the top, right, we notice something. And there's actually a good example of this. There's this Khan Academy video that I'd like you guys to check out that does a good job of explaining that. I'd also like to talk about what happens kind of if we look at it from this side, right? You guys can kind of see that. See how it appears kind of a little bit broken, right? That's kind of a little bit strained. So what's actually going on there? Is that the same kind of thing? Can we explain that in the same way, right? Well, sure enough, we can. If we consider this here, right? This is the kind of the phenomenon that we're seeing, right? The straw kind of comes in and then it breaks, right? Somehow. So what's actually happening there? Well, what that means is if we're looking just normally from above, right? Above the glass, above the water, right? Then this light wave can just kind of travel straight to our eyes, right? Because there's nothing, it's not really changing medium, so it can just travel there just normally, right? But if we actually see it, right? Once it goes below the water, we see it kind of to the left of where it is. So this is an overhead view of what we're kind of seeing. We see it to the left. What that means is that we're seeing, right? We're seeing the straw as essentially being right here to the left of where it actually is, right? Well, what that means is that this light leaving the straw is actually coming to the surface of the glass and it's actually bending, right? It's bending and then it's traveling back in this direction towards our eye. Okay, so our eye sees this here, but this area right in here, this is where that bending is happening. Well, if we think of what's going on, right, it's kind of coming in here. It's going from a slower medium, water, to a faster, right? Which side is going to speed up first? Well, it's going to be this side of the wave is going to speed up first, which is going to cause it to shift in this direction, right? So this phenomenon as well, right, seeing the straw kind of like broken like this can also be explained by the same kind of understanding of refraction, right? It's a very useful thing. So that's the main basics on refraction that you guys need to know is when you change and you go from one medium to another, right, light changes speeds. And because it changes speeds, if it's entering at an angle, that can cause it to change its direction, right? And we can actually calculate that. It's a very predictable kind of thing and explains a lot of kind of interesting phenomenon. Now, a few other things that I do want to talk about, cool or good things to know. One thing is that, once again, going back to our glass of water, never going to leave it alone. What I'd like you guys to do is if you kind of look at it from like kind of lower angle here, not from straight below, but from a lower angle, and you can kind of see some interesting stuff. And if you put your hand over it, you may notice you can't really see your hand behind the water there. So what's actually going on? It's almost like a mirrored reflection. And this is actually a cool thing. When fish are looking up at the water at a certain angle, they actually can't see. And we can model this looking at this here. So if we're going from water to air, right? So something that is slower to something that is faster, there comes this point called the critical angle, which is right, in this case, right there. Boom, that's critical angle. So if between water and air, the critical angle is right around, looks like 50 degrees, give or take, right? So if it's coming in at 50 degrees or greater, you'll notice it does not pass through the medium, right? Here, there is some light being transmitted, but here it's being totally reflected back into the medium. It's almost like a perfect mirror. You'll see this with prisms if you guys ever get a chance to kind of look at one of those, right? You look kind of inside, and at certain angles, you're not actually able to see through it, right? It's really quite incredible. You can see it with the water, as you did right there, right? So you can imagine, right, kind of flipping this image here, and you're looking up, and you can only see a perfect reflection. But at steeper angles, you can actually see through to the other side. And if you look straight up through the bottom, you'll notice it's just like looking. If you look straight up through the bottom, right, you can see the ceiling. No problem, no issues there, right? So this, right, this is something that's called total internal reflection, right? When going from a slow medium to a faster one at a certain angle called the critical angle, all light is reflected, none is is transmitted. Right, which is kind of cool. So that's what's actually happening there. That's called total internal reflection. That has some cool kind of applications when it comes to, if you guys have ever heard of fiber optic cables being used to kind of transmit electromagnetic waves. What you have is you essentially have a long glass cable, right? And because of the kind of unique properties, the unique kind of critical angle of glass relative to like air, a lot of surroundings, you kind of get something where it only passes through in a straight line, so you can't really see. I'm not sure how this demonstration is. Let's try this. Right. So it goes straight through here, right? But if you look kind of from the side, you can't really see the light kind of through. It's all just passing through. And you can create some really cool patterns with this. Let's see if I can actually get it here. Right. So for example, I can get it almost like a flashlight, where it's only reflecting. Here, maybe it's even better if I can do it like this. There we go. Right. It's only passing through in kind of one straight shot line, right? And it's reflecting and creating this kind of pattern there, but it doesn't really scatter outside of that, right? It's really, really interesting. So that's total internal reflection. It's a pretty neat little thing. Very cool to kind of mess around with. Another demonstration. So this is another cool thing that happens. Is the reason why we can see clear things like this prism, for example, is because of either the reflection or even just like glass things like this. The reason why we can see them, even though it's like they transmit most of the light waves, is because of how they actually bend the light waves, right? Now, because you're going from one medium to another, those light waves bend, as we kind of talked about. They refract, right? Now, what's interesting here is I have a little glass full of oil, right? Now, oil happens to have approximately the same index of refraction as glass. So if I stick this glass prism in here, right, you guys will notice something kind of interesting, hopefully, if it works out. Right? It essentially seems to disappear, right, other than that little glass, that little bubble that was kind of trapped there. But you can't actually see it, right? And why can't you see it, right, versus when you can see it above the glass, but you can't see it when it's in the glass? Well, that is simply because, right, they have the same index of refraction, right? So as the light passes through the glass, through the oil, through the prism, it doesn't actually change. It doesn't bend, so we don't actually see that it's there, right? So if you were to take like a a bubble of water and put it in like a bubble, or put it in underwater, it's like it'd be the same kind of thing. It's really kind of neat, really kind of an interesting thing. So why do the glass disappear in the oil? Well, because, or rather since, they have the same, or about the same, index of refraction. The light waves were not bent or refracted. So we could not discern the outline of the glass. Right, in other words, we couldn't see it. You can actually see this if you go from like one material to another. Just, the light waves don't bend, so we don't get any kind of signal or any idea that it's passing through anything at all. Okay. And the last one that I want to bring up is because we can use these prisms, right? If we take white light, we can use these prisms to actually reflect a kind of rainbow down, right? We can use these kind of split visible light. So what is happening when we use something like this, when we have light that's going through here, right? White light being all kind of the wavelengths of visible light, all those different colors, and it goes through here, and that light bends. But what is it? Why is it in that bending that we get the light to actually separate out, right? And we can actually kind of see that if you guys mess around with this in this prisms example, right? You'll notice if we have this prism, we're going from kind of fast to slow, so the left side kind of slows down first, or the right side slows down first, which bends it to the right, and then as it's leaving, right, the left side speeds it first, which bends it to the right even further, right? So we have this light bending a good bit. It's bending once at this interface, and it's bending once at this interface. Now, right now, it's just a single laser. I could look at it as multiple laser beams, and they're all kind of doing the same thing in a line, or I can look at it as visible light. And if I look at it as visible light, I see that after a distance, right, they start to kind of separate. And the separation actually starts to occur here, but we only really get a noticeable rainbow kind of the farther away you get. And if you could extend this further and further, they'd be spread out even more. Right, so what's happening in this case? Well, what we can imagine is that in here, right, we know that in the visible light spectrum, red wavelengths have the longest wavelengths, right? The longest wavelengths in the kind of lowest frequency, right? So there's fewer of them coming by per second. Whereas blue or violet, right, have higher, right? They've got shorter wavelengths and higher frequencies, right? So there's more of them passing by per second. Well, if we can imagine in this case here, right, depending on the wavelength and the frequency, right, the more kind of waves that are going by per second, the more of a bend you actually get. The shorter that those wavelengths are, the more of a kind of transformation, the more of a bend that you get when you come to that boundary, right? So because of that, because the blue light actually and the violet light bends more than the red, we get this gradation where all of the wavelengths of light kind of separate out. Now what is really cool too is if we take another prism and we kind of reverse this and do the exact opposite, right, you'll notice that the light waves start to come back together and we kind of run out of space here, right? But eventually the light waves come back together into forming just one kind of regular normal light wave, right? Which is actually kind of cool, right? So we can actually bring them back together by going through the same kind of process in reverse, right? So that's kind of cool. So what's actually happening here? Why does light split up to form a rainbow? Well, the long and short of it is that, right, as light waves refract, waves with longer wavelengths are refracted or bent less, while those with shorter wavelengths are bent or refracted more, right? Thus causing all frequencies, all wavelengths of visible light to separate, right? And that's that. That's all there is to it. So that's the long and short of reflection, or refraction. The key thing being that when light goes from one medium to another, right, it slows down because it slows down, right? If it's coming in an angle that causes it to bend, right? Different wavelengths do bend more or less. The shorter the wavelength, the more it's going to bend, and that's because essentially it's like having a lawnmower that instead of being like a long wheels or having big wheels, it has really short wheels. Right? So if you could imagine this lawnmower having even really tinier wheels or smaller wheels, it's going to start to bend a lot more than one that has bigger wheels, which aren't going to be as affected by that change in medium. Okay, so that's refraction. We're going to talk about that a little bit more next class when we start talking about lenses. We'll talk about these things and how they work. We'll talk about your eyes and how they work. We'll talk about my glasses and how they work, and how they use this kind of law of refraction and how that actually works to actually allow us to see things in more meaningful and useful ways. So, hope you guys enjoyed. Hope you guys are doing well, and I will see you guys later.